Hello again, physics friends. Today we are going to talk about central force motion, but now with two bodies instead of one. But before we dive into that, let's just do a recap of the main results that we found for central force motion with one body. So we have our coordinate system and an origin. We have a mass moving relative to that origin, and the position vector is given here. And we found that if this mass experiences a central force, there's no associated torque, and therefore the angular momentum is conserved. Or using the language of the Lagrangian, we found that the coordinate phi does not appear in the Lagrangian, therefore the associated generalized force is 0, meaning the generalized momentum associated with phi is conserved, and that was the angular momentum. So we can call that angular momentum L naught, which we understand is r cross v, which is mr squared phi dot. So that's a constant. When you combine the two Euler-Lagrange equations for r and for phi together, using this constraint, we arrived at a single differential equation for the r coordinate involving only r, and constants, but no phi. And we found that we could write this as something that looked like Newton's second law, where mass times an acceleration-like term is equal to minus the gradient of a potential. That's like a force. And the thing that plays the role of the potential is not the actual potential of the interaction, but rather a combination of that potential and the so-called centrifugal term that accounts for the angular motion. Remember, L naught has in it a phi dot. So there's angular motion embedded in this equation, but it's embedded in this constant L naught. So this looks like a differential equation. Well, it is a differential equation for r, but this looks like a one-dimensional problem. Okay, what we're going to find is that with the two bodies, rather than having basically an object fixed at the origin and a second object moving around, if we allow both objects to move relative to the origin, we're going to arrive at the same main result, that we can have a one-dimensional equation with an effective potential. So that's where we're going today. Before we get too deep into the mathematics of two-body motion, let's just make sure we have kind of a picture in our heads. So the work that we're going to be doing is not only applicable to gravity, but it certainly does apply to gravity. So let's consider two stars, like a binary star system, and let's assume that these two stars are equal mass. So if we let mass 1 and mass 2 be the same, then we have the following. The system is going to, these two stars could orbit each other, so to speak, but actually they're going to end up orbiting the center of mass of the system in green. And the center of mass will be midway between the two masses when the masses are equal. So you might imagine a velocity vector for mass 2 and a velocity vector for mass 1, and those velocities would always be equal and opposite. In the frame in which the center of mass is not moving, the momentum of mass 2 is going to balance the momentum of mass 1 so that the total system momentum is 0. Okay. Even if the two masses are not the same, we can get a sense for what the motion will look like. So here we have mass 2 and mass 1, but now I've made mass 2 bigger than mass 1. So the center of mass of the system will be closer to mass 2 than to mass 1. Well, one possible trajectory here is that mass 2 moves in a circle about the center of mass, and mass 1 also moves in a circle about the center of mass, like this. And if the center of mass is at rest, in other words, if we work in the center of mass frame of reference in which the center of mass doesn't move, then these two objects will move in such a way that they are always on opposite sides of the center of mass from each other. So if mass 2 moves down here and mass 1 moves up here, sometime later mass 2 will be there, and you can tell that mass 1 has to be on the other side of the center of mass, like so. Okay. So the center of mass won't move. The two masses have to always be on a line connecting those 3 points, the two objects in the center of mass, and the system will orbit in this way forever. So notice that in this case, there's also no external force on the system. There's no external torque on the system. All the motion is planar. So all of the things we learned about for one-body motion are going to apply here. And the next thing we want to do then is write out the Lagrangian for a two-body system and show that it reduces to a one-dimensional problem again. Okay, so in the two-body system now we have the following geometry. Neither object is at the origin, both objects are free to move, and we have mass 1, mass 2 with position vectors r1 and r2, and the system will have a center of mass, and that center of mass will be somewhere on the line that connects the two objects. Now we can write down the Lagrangian for the system. It will involve the kinetic energy of mass 1 plus the kinetic energy of mass 2. And then we subtract off the potential. And right now we haven't specified what the potential is other than it's a central potential. So it looks like we might need 6 coordinates, 3 for mass 1 and 3 for mass 2, but we're going to change our thinking slightly, and instead of working in the coordinates, well, instead of using the position vectors for the two masses, we're going to use a pair of other position vectors. Okay, the first thing we're going to do is we're going to define capital R, the position vector of the center of mass. So we can draw that in our system here. So I'll do these in purple. Okay, so capital R is the position vector to the center of mass. And the second vector we're going to define is a relative position vector. It's a position vector, turns out, from mass 2 to mass 1. And we'll define it as the difference of R1 and R2. If you're having trouble seeing whether that vector points from 2 to 1 or from 1 to 2, I like to think of the position vector in the following way. We can rearrange this equation to say R1 equals R2 plus R. So in order to get to mass 1, you can either do R1 or you can go R2 plus R. So that tells me that R's got a point from mass 1 to mass 2, like so. So we now have an expression for capital R and lowercase r in terms of the masses and the position vectors of each object. We want to invert that relationship and write R1 and R2 in terms of big R and little r so that we can rewrite our Lagrangian in terms of big R and little r. So let's see how we can do that. So we have the following. We can write R1 as center of mass position plus an offset from there, and center of mass position minus an offset from there. So let's see how that plays out. Right, if we want to get to mass 1, that's R1, we first go from the origin to the center of mass, that's the position vector R, and then we want to travel in the plus R direction, and we want to travel a certain distance, that distance given by m2 over m. So that's a number less than 1, where capital M is the total mass. So we want to travel not the full length R, but just a fraction of it. To get to position 2, we want to first go to the center of mass and travel in the minus R direction. Again, not the total length R, but a fraction of it. So you can convince yourself that the proper fraction in both of these cases is m2 over m or m1 over m. I'll leave that as an exercise for you. So once you've made these substitutions, we can now rewrite the Lagrangian in terms of our center of mass and relative position vectors in the following way. 1/2 big M, big R dot squared. So that talks about the kinetic energy of the system, kinetic energy of the center of mass, basically, plus 1/2 times this new quantity mu times the relative position vector R dot squared minus the potential. So we have this new term mu that we should define. It's called the reduced mass. Okay, and it is defined to be the product of the masses over the sum of the masses. And if you've worked with resistors in parallel, mu is like the mass equivalent of resistors in parallel, where if you have two resistors in parallel, the total resistance is the product over the sum of the individual resistances. So let's think a little bit about the reduced mass in a couple cases. So for our first case, let's consider the limiting case where mass 2 is much bigger than mass 1, which basically means mass 2 is barely going to move. And in that case, we can treat mass 2 as being at the origin. And so we'll have something like this, where we have an enormous mass 2 and a little mass 1. And we have a position vector, R, which points from mass 2 to mass 1, but we can really think of r is effectively the same as r1, which is the position of mass 1 relative to the origin. So one consequence of mass 2 being huge is that r is approximately equal to r1. And we can also see that the reduced mass is going to simplify. The reduced mass is the product over the sum. If mass 2 is much bigger than mass 1, then that denominator becomes basically just mass 2, because you have a big added to a tiny, you just get the big back. And mass 2 will cancel, and so the reduced mass is mass 1. So in the case where you have a highly discrepant masses, then the reduced mass is effectively equal to the smaller of the two masses, in the same way that resistors in parallel behave as if it was just the smaller of the two resistors, in the case where the two resistors are very different from each other. In the second case, let's consider the two masses equal to each other. So the center of mass is midway between. So if you have mass 1 here, mass 2 here, the center of mass will be right in the middle between the two. Remember, the r vector points from 2 to 1. Okay, and if you set your origin to be at the center of mass, then you have two position vectors. R2 points to mass 2 and R1 points to mass 1. So you can see that the magnitude of R is twice the magnitude of R1 or R2. And you can also see that the reduced mass, which is the product over the sum, is going to be m squared over 2m, or 1/2 of any individual mass. Again, similar to the parallel combination of resistors. If you have two identical resistors, their parallel combination is half of the initial resistor value. Okay, so this is just to give you some sense for a couple limiting cases for a two-mass system, and to give you a sense for what the reduced mass is in limiting cases where one is much bigger than the other, or when they are equal in mass. So now that we've talked a little bit about the meaning of the reduced mass, I want to come back to the Lagrangian and focus on this first term. Right, this first term is saying how is the center of mass of the system moving? Okay, well, this system is composed of these two particles. Maybe there's a force in between them, indicated by the potential, but there's no external force on the system, or at least let's assume that there's no external force on the system. And if there's no external force on the system, that means the center of mass is either at rest, in which case r dot will be 0, big R dot will be 0, or the center of mass is moving but at a constant velocity, in which case this is a constant, capital R dot squared. Now we know that the Lagrangian, if you add or subtract a constant, nothing changes in the equation of motion. So we know that this first term, 1/2 capital M capital R dot squared, is a constant. Okay, that means we can get rid of it. Okay, what does it mean to get rid of it? Well, one way to think about that is that you work in a coordinate system in which the center of mass is at rest. So you can always, without any loss of generality, you can choose a coordinate system or choose a reference frame in which the center of mass is at rest. Okay, in other words, big R dot is 0. And in that case, we can get rid of that first term in the Lagrangian, and our Lagrangian becomes 1/2 mu r squared, r dot squared, minus the potential. This is the Lagrangian for our two-body system. And now what we can do is draw an analogy between that Lagrangian and the one for the one-body system. Right? Notice it's exactly the same form. Right? It's a mass over 2 times a position vector dot squared minus a potential. Same thing here, except we've replaced the mass of the single particle with the reduced mass of the pair of particles. And now this position vector, which used to be the location of the mass relative to the origin, now this position vector that we're talking about in our new Lagrangian is the relative position of one mass relative to the other. Okay? But everything that applied in the one body case is also going to apply here because the form and structure of the Lagrangian is the same. Phi is still not present in the Lagrangian, so the angular momentum is still conserved, okay? So we still find the angular momentum is constant in the two-body system because phi does not appear in the Lagrangian, okay? We don't have to go through all of the Euler-Lagrange equations and take partials. We know that the answer is going to be this because the form of our Lagrangian is the same as it used to be. So we know that we're going to have, instead of m r double dot, we'll have mu r double dot is equal to minus ddr of the angular momentum squared over 2 mu r squared plus u of r. Okay, and this L naught term, just as it was before, is the angular momentum, mu r squared phi dot, and it's a constant. So this is great. All of the physics that we learned about for a single body applies to a two-body system, and here is the equation of motion. And the term in square brackets is also is going to play the role of U effective once again. So we're going to talk about effective potentials for central force motion, and in a future video we're going to talk about how to think about and plot and interpret plots of this effective potential. That's all we have for today, but until next time, take care and be well.